Welcome to week 9. This is the first video of the 3 videos for week 9, and the topic is network clustering. This is chapter 6 in your textbook. We've been talking about clustering quite a bit. We know how to find the clustering coefficient, and we know that the clustering coefficient of a graph ranges from 0 to 1. With 1 closer to 1 indicating higher clustering and closer to 0 indicating not clustered. So what does a cluster mean exactly? Well, the clustering coefficient we're saying is a measure of how much the graph is clustered, where a cluster is a highly connected subgraph. So if the clustering coefficient is high, that means in general that most of the vertices occur within a cluster. And how we interpret the cluster depends a great deal on how the graph itself is constructed. Since most vertices occur within a cluster, then we can think of the entire network as a network of interacting clusters. So this gives us a global view of the network. In each cluster, then we can look at the density of each cluster, or look at the role of the particular vertices within a cluster. And there we have a local view. So by connecting the clusters, we have a way of examining the graph in both a local and global standpoint. There are different types of biological networks that we're going to be looking at. One is a protein interaction network, where each vertex represents a protein, and 2 vertices are connected by an edge if the corresponding proteins are known to interact. We also may look at some gene-gene interaction networks, where each vertex represents a gene, and there's a connecting edge if the genes are known to interact. Actually, this may be a little misleading, because with the protein interaction networks, 2 proteins do actually physically come together and bind and perhaps form what is called a protein complex. The genes do not bind to each other. Rather, there's an inferred relationship between the genes, where 2 genes are connected by an edge if they are within, or if it has been determined that they are involved in the same processes. So microarray analysis of genes, that 2 genes are known to be, say, upregulated during the same types of processes, and there's an inferred relationship between those genes. So getting back to cluster analysis, most cluster analysis in the literature has a statistical method for determining the clusters. There is not as much in the literature on cluster analysis that uses both graph theory and theoretical computer science. But those 2 topics, which blend to give us things like graph algorithms, are a useful tool, and so that is the approach that we're taking here. There are many algorithms in computer science that use graph traversals that have the potential to help with cluster analysis. One of the kinds of algorithms that you find is called a greedy algorithm. So we will illustrate a greedy algorithm by taking this graph and finding a maximum weighted spanning tree. Now in the literature, you usually find a minimum weighted spanning tree, but to illustrate it could be maximum as well as minimum. The algorithm still works. we're going to find a maximum weighted spanning tree. So the term greedy comes from the fact that at each step, we're going to choose as much as we can. So since we're seeking a maximum weighted spanning tree, we're going to choose the heaviest edge that we can, because a spanning tree is a subgraph. Since it's a tree, it's connected and it has no cycles. And since it's spanning, it means that we have to use every single vertex. So we want a subgraph that uses all of the vertices, that's connected but no cycles. And in addition, we want to be able to add the edges of this spanning tree and get the maximum possible sum of the weights of the edges. So we will choose the edge AB because it has the maximum weight of 7 and start to build our tree. So far we just have one edge. Since we don't have a spanning tree, we'll choose another edge. The next edge we choose is 6. It has a weight of 6, and that's the edge EF. We don't have a cycle, so we can keep it. We're not connected, so we keep going. We choose the edge weighted 5, which is FD. We don't have a cycle, so we keep it. We're not connected, we keep going. We can choose from 2 edges. We can choose either EC or FC, since they're both of the next highest weight. If we choose, let's see, CF or FC, then we don't have a cycle, but we're not connected. We haven't used all of the vertices, so we keep going. The next one, the next heaviest edge, is EC. But now that generates a cycle, ECF. So we do not accept the edge EC. The algorithm will discard it because that generates a cycle. So far we have the edges that weigh 7, 6, 5, and one of the edges that weighs 4. Those are the vertices A, B, C, E, and F. And also D, because we have the edge FD. The only thing is, we don't have a spanning tree because the tree is connected, and the graph that's induced by the edges so far has 2 components. So we choose one more edge, and we choose the edge BD. Now we have a spanning tree, and we claim that if you add the weights of the edges, that is a maximum among all spanning trees. So let's add those. That's 7 and 6 and 5. So that's 18, and 4 is 22. And then another 3 is 25. So we have a weight of 25. Notice that a different spanning tree could be if we choose the vertex C and all of the edges incident to the vertex C. Since C is adjacent to all of the other vertices, this is a spanning tree. So we would have the edge AC, BC, DC, FC, and EC. We would have a star. It's a connected subgraph that spans the whole thing. So what is the sum of the weights of those edges? These are the edges incident to C. So we have 3, and 3 is 6, and 4 is 10, and 14. Quite a bit less than our maximum weighted spanning tree. So a graph can have a large number of different spanning trees. So among all the spanning trees, the greedy algorithm can give us either the maximum weighted or the minimum weighted if we choose at each step the maximum or the minimum weighted edge that we can possibly choose, that doesn't generate a cycle. Now, I mentioned that typically in the literature, it's the minimum weighted spanning tree, because the original application of this, the weights indicated a cost. And of course, we always want minimum cost. But in our application, we might want a maximum interaction or some other thing, so it's equally applicable for maximum as well as minimum. So just to illustrate the greedy algorithm again, this time what we want to do is to find a maximum independent set. So we're not going to be adding the weights, we're simply going to have the cardinality of the set to be maximum. So in that sense, it's greedy, because we want to choose vertices so that we induce the minimum number of edges so that we can have the maximum size independent set. So we could choose, say, the vertex A. If we choose a minimum degree, we could choose all but C. If we choose C, the algorithm would stop, because what we're building is an independent set. So at each choice we check, if we add this vertex to our set, do we induce an edge? So if we start with the vertex A, that's the first one in our set, then we will choose another vertex of minimum degree. If we choose B, the algorithm will say no, that induces an edge, and we choose E, the algorithm says no, that induces an edge. So we would discard those immediately, and we have and C as well. So that just leaves D and F to choose from. We can choose either one, but once we choose either one, then that's all we can choose. So let's say we choose D, and so our maximum independent set returns with A and D. Now there are a large number of different independent sets, but they all have one thing in common. They all have the same number of vertices, in this case 2. So we're going to be able to use some graph algorithms to find different subgraphs with different properties of a network. And why are we interested in graph algorithms for identifying certain kinds of subgraphs? Because we're interested in network clustering, but a cluster is really a subgraph. Now, you say, well, an independent set, isn't that the opposite of a cluster? And that is true. But if it has no edges, then what does the complement have? So if we have an algorithm for finding a maximum independent set, then in the graph's complement, we've automatically obtained a cluster. So the next time we'll talk about clique-based clustering using these greedy type algorithms.